Hello and welcome to Denmark. In fact, welcome to Europe. As you might have guessed from the title of the video, today we are making maps, or we are making a map, and well, this right here is the finished product already, and well, it's quite a detailed map. I mean, just look at all those tiny little islands. Look at all those grasslands and deserts and mountains and rivers. It's basically the rivers. And well, the second best part about this map is that our little country ball here can interact with the map. Like if we move into a river, we get this adorable little flotation device. We also move slower across rivers or ocean. We also move slightly slower across mountains. That's the second best part about this. The best part about this is that it runs so smoothly. I mean, I can move the camera way around without any noticeable frame lag. I can zoom way out, or way in, without any real lag, and that's great because the whole reason I wanted to make this map in the first place is that I want to make a game. Specifically, I want to make a real-time strategy game set in Europe, because Europe is the best continent, using the aesthetic of country balls fighting each other on a map like this one, because I like the country ball aesthetic and I like maps. And over the next insert video length in minutes, I want to show you how I made this map from a bunch of scientific data. So the first thing we are going to need is a map of the coastline, or a map of what is land and what is water. And well, we can get that from here. This is naturalearthdata.com, which hosts a collection of public domain map data. Let's see what they have to offer. We want a physical map, and we of course want the highest resolution available. So let's click on physical. Now we can choose a map with the coastlines as line or land as polygons. I am going to go with the land, but we could totally also use the coastline map for this. I actually already downloaded this file, as you can see. Let's take a look at it. It's a .shp file. Let's take a look. Sorry about that. Beautiful. It's a bunch of binary chunk. It's a big bunch of binary chunk. Yeah, we are probably going to have to read up on exactly how this format works, and thankfully I already did that. So I made this little infographic explaining how the shapefile format works. And essentially the things to understand is that it's a binary format which includes a bunch of big Endian 32-bit integers and a bunch of little Endian 32-bit integers and a bunch of floating point 64-bit numbers. And yeah, you heard me correct. We have both big Endian and little Endian integers. If you don't know what that means, Endianness essentially means what order the bytes in a number is written in. You can think of it a little like whether the number 100 is written as 1, 0, 0, whoopsie, can't see that, 1, 0, 0, or if it is written as 0, 0, 1. The first thing is called big Endian, and the second thing is called little Endian. And usually a file format sticks to either one or the other. It's a bit unusual for a file format to include both, but shapefile is one of those formats which includes both. I guess it's for purely historical reasons, but it's still pretty annoying to work with. Anyway, that's just something we have to think about. Besides that, the shapefile contains a file header which is exactly 100 bytes each time, and it contains a bunch of stuff. It contains the file length and the minimum and maximum longitude and the latitude this shape covers, and it also includes the shape type code, which in our case is going to be either 3 or 5. 3 for pure lines and 5 for polygons. After the header we have a bunch of records of variable length. These records also have a header of their own, which includes the record ID, the record length, and the shape type code, which is completely redundant because it has to be the same as the shape type code in the file header itself. But after the record header we have the record data, and that's a bit different from shape type to shape type, but for polygons and polylines specifically it's the same. It's again the minimum and maximum longitude and latitude of this record in particular, and then the number of parts and the number of points and the array of parts and the array of points. And what parts and points means is that, well, essentially points are longitude and latitude points. For instance, you could have a point here, and a point here. And let's say this is point number... Okay, gotta scale that down slightly. Let's say this is point number 0, this is point number 1, and this is point number 2 in the array of points. And then the parts might include a sequence like this. Let's say 1, 0, 2. That means that we have a line from point 1 to point 0, from point 0 to point 2, and depending if this is a polygon, we also have a line closing this going back to point 1, but if this is just a line and not a polygon, we don't have this closing line. So that's how the shapefile format works, and it is fairly easy to write a C++ program for loading shapefiles, which is, well, what I have right here. I must admit I used a little bit of AI generated code for reading big endian and little endian numbers. That's just easier that way, and it's such a simple task that even an AI can't mess that up. And well, I'm not going to go through everything. It's basically everything I talked about. We read the header, then check what shape type we have, then we read all of the file record by record. We read the record header, and once we have the record header we read the points and the parts, and yeah, we save them as some sort of polygons we can use inside this C++ program. Anyway, that's all there is to say about the shapefile format. It's just another format. So one problem with the shapefile format, or one issue with it, is that it is a vector format. It is a collection of points and lines between points, making up polygons. But I want a rasterized image. That is, I want an image made up of pixels which are either on land or in water. I'll use white pixels for land and black pixels for water. The reason I want this is twofold. Firstly, it's easy for checking whether you are on land or in water in a game, to just be able to look up in a rasterized texture. No calculations required, just check is the pixel black or is the pixel white.
and for the graphics engine, rasterized graphics is also preferred because the Simple Direct Media library I'm using for graphics in C++ is fundamentally a rasterized graphics engine. So given a bunch of polygons, how can we check if we are inside land, inside one of these polygons, or in water, outside these polygons? Well, one way is to say pick a point we are interested in and draw a line to that point from any edge of the image. Will do. Let's do this edge because that's what I do in the algorithm, and count how many times we cross the border of a polygon. If we cross the border of a polygon an odd number of times, we know we are inside a polygon. If we cross an even number of times, like 1, 2, 3, 4, we know we are outside a polygon. And this is thankfully trivially easy to implement in C++, and well, I've done that in this program here. Right here we have the load shapefile code, which loads the shapefiles into a vector of polygons, which is a class I made to hold these. And this polygon class has a function called inside, which given a longitude and latitude coordinate uses the algorithm I just described. Raycasting it's called, to check if it's inside or outside a polygon. And well, for every pixel we loop through every polygon and check if we are inside of it, and if we are inside anything, we make the pixel white 255 value. If we are not inside, we make it black 0 value. And that's essentially how we make a rasterized image of this shapefile. Now, one slight complication is that we have way too many pixels to just do that in a giant loop, one pixel after the other. We have 16,384 by 16,384 pixels, because I thought that was a nice round number. That's a lot of pixels, so we are obviously going to use some degree of multi-threading, and this can be done very easily in modern C++ by using the std for each function with the parallel execution. This means that we use as many threads as are available, which is 20 in my case, on all the rows in this image here. This of course speeds up calculation by a factor of 20, so that's very welcome. It still takes 3 full days for this program to run, so I'm very glad I bothered making it multi-threaded. Anyway, when we are done, we save it as a PNG. This is just how you do that using the libpnt official PNG library. Yeah, I don't think there's anything more to say other than the fact that I'm not doing this on the entire planet. I'm only looking from 13 degrees west to 44 degrees east and 75 degrees north to however far south you need to go to have a square image. And well, when I run this 3 days later, I have an image like this rather detailed map of Europe, map of all the land and water in Europe and North Africa. You can see there's a lot of land in the Sahara, like really a lot of land. This doesn't include lakes and rivers, as you can obviously tell. We're going to have to add them later. But I am still quite satisfied that this is a good starting point. We are definitely going to need this map for creating for creating our map, but let's talk about the rivers next. So rivers, that's thankfully one of the many things Natural Earth Data.com offers. Right here we can get the rivers, a bunch of big rivers for the entire planet, and a bunch of smaller rivers in Europe specifically. This dataset doesn't include any rivers which are already in this dataset, so we are going to need both. Now, I have already downloaded those files, and those are just shape files like before, so it's we already have the code for loading them. And let's see. And this time the only difference is that we are not dealing with polygons we want to check if we are inside of. This time we are dealing with the rivers where we want to know exactly how close we are to the river. So not only can we know whether or not we should color the final map pixel blue because we are in water, but we also know if we should color it green because the rivers in North Africa especially are much more fertile than the surrounding desert. But well, in principle it's trivially easy to make a distance finding function in C++ which returns how close we are, and then we can just scale the pixel from black when we are at the middle of the river to white if we are further from the river than in this case 0.1 degrees. And in principle this works, but in practice it doesn't really work that well, because it took 48 hours to run, and these are the results for the small rivers. As you can see, the dataset, the data is not very good. There are a bunch of holes in the rivers, and I don't know what causes these holes. Maybe there is something wrong with my distance finding algorithm, or maybe there is something funny going on with the dataset. Either way, this is completely non-usable, and the worst part is that it takes 48 hours for this program to run, so debugging it is quite difficult. So difficult in fact that I decided it was easier to just manually trace the rivers by hand instead, and this is what I have done in this file. I traced the rivers in a drawing program. These are the big rivers and the small rivers overlaid on the top of the land and water dataset. Yeah, it feels a little like giving up manually tracing the rivers, but as I said, it was much faster to do this way, and I am quite satisfied with how it turned out. One little annoying thing is that the detailed dataset ends here in the Middle East, so I don't get small rivers around the Nile or in North Africa, but that dataset simply didn't exist. Anyway, we got a bunch of rivers now. Now it's time to think about other details we want to add to the map, like for instance, we are not done thinking and talking about water yet, because we also need to color the map either green or brown, depending if it is desert or grassland. And to do that, we need to look at the precipitation, how much rain each area gets. So let's do that now. So it can be a little hard to find this kind of data, and I would gladly admit that the way I found this precipitation data was by asking an AI chatbot for links. You might think that's a bad way of going about this, but if you specifically ask for links, AI chatbots are actually quite good at providing links. These days, most of the links they provide even exist. of course, you shouldn't believe any of the triple or hallucinations the AI actually says. You still need to check out the links yourself, download the data and try the data out before you know if the data is any good. And I have tried all these datasets out, and the one I found worked best was the one from worldclim.org. This precipitation data, obviously we want the highest resolution possible. If we go ahead and download that, we find that it's a TIFF image. Here we have it right here. It's actually a TU-TIFF image, which is just a regular TIFF, but with more TU spatial data included. And well, I'm not going to write my own TIFF loading algorithm. I'm just going to use the TEDL library here, which allows us to, well, open TU-TIFF data and get all the relevant data out. And this is what I do in this program, and then I simply turn it into a PNT image. Oh yeah, after cutting out the part of the world I am interested in, because this is a 40,000-ish, yeah, 43,200 by 21,600 image of the entire world. I need to cut out just Europe, and then when I'm done with that I need to scale it up slightly, but that's easy to do, especially if you are like me and have no shame whatsoever, because I just used AI generated bilinear image scaling to scale it up. Yeah, I know I have no shame, and the AI probably stole this code from some hardworking human somewhere, but I wasn't able to track down the original source for this. Anyway, when all is said and done, we get, well, this image here. Let's just open that. Sorry, I should have prepared myself a little better. Here we have it. This is what the precipitation data looks like. Now, one problem with this dataset is that the precipitation is set to max value for the oceans, which is yeah, not true. The data is just missing for the oceans, but the oceans are going to get cut out anyway by the water map, so this shouldn't be a problem. Oh yeah, one fun thing about the TIFF format is that it's a floating point data format, so the data at any pixel can be anything really, and I want this to be a PNT image, so I want this to be a PNT image, so I scaled the data to be between 0 and 255, where 255 of course is the rainiest, whatever place in Europe happened to be the rainiest according to the dataset. And that's basically how I got the precipitation data. Getting the height data is equally easy. The height data is something I need so that I can tell where the mountains are, is equally easy. Let's see, in this case I just googled the word topography and got the link appeared to have died since I last checked it. Apparently the link I used doesn't exist anymore, but I did get and that data was already a PNT image. Let's see, the data is here. I just had to scale it up slightly, which I did with another C++ script. Let's see. Yeah, I'm doing this a little off the cuff. without any preparations. This is the height map after I scaled it to the correct size, and again made sure the highest place in Europe got to 55 value, and the lowest place of sea level got 0 value. And now we actually have everything we need to make the final map. You know, let's just look at that right away. We have this generate the final map program, which loads a bunch of PNGs. We load the water map, the precipitation map, the height map, and the river maps. I have one map with the large rivers and one map with the small rivers. Then after doing some basic sanity checks, we want to use what I call color ramps to essentially interpolate the colors between different color ramp points depending on what the height is, or what the precipitation is, or what the water map is saying at these points. I call them color ramps because that's what they are called in the 3D animation program Blender. So I'm just copying the terminology from that. Anyway, I loop over all the pixels in the image and check if they are water, or if they are fairly close to a river. I just make them blue. I don't use any different shades of blue depending on the depth of the ocean, because that wasn't included in my data set. Otherwise, I first use the precipitation data to make a color ramp based on, well, the precipitation, how much it rains. I ramp it from at no precipitation brown to green at the highest precipitation. Oh, and I also include the river map mode in this color ramp, so that well, close to the Nile stuff becomes green as well. After that, I make another color ramp based on the height map, where I map the color from whatever the results of the precipitation color ramp was to gray at the highest elevations. And well, this isn't particularly slow. I don't even use multi-threading here, it's so fast anyway. And let's take a look at the results. Well, we can take a look at the results here in an image editing program, and here we have it. Here we have the final map, which you anyway saw at the beginning, but there is still a problem with this final map here, and that's that it's all one big image. It's one gigantic 16,384 by 16,384 image, and I physically cannot create a texture this big. My graphics card literally cannot handle a texture that big. Your graphics card might be able to handle this, but handle a texture this big, but most computers probably can't. And besides, using a single texture this big is extremely wasteful, because right now we are zoomed so far out that we can't see most of the details anyway. And if we zoom in so we can see all the details, then most of the image is going to be outside the screen. So we need some kind of better way of handling this. And well, the way I'm going to handle this is I'm going to use tiles. If we zoom in for a minute, and that's quite a difficult thing to do because my mouse scroll wheel is currently broken. I'm trying to zoom in, but it keeps zooming out. Okay, I think we are close in now. I'm going to use tiles, which are individual smaller images. For instance, we could have a tile with just Denmark here, a tile with, they should really be the same size, a tile with odds of northern Germany here, a tile with a bunch of Germany and Poland, a tile with the western Baltic Sea, and we only need to render these tiles if they are inside the screen. I mean, if we are like this, we don't need to render the eastern tiles at all, and like this we don't need to render the western tiles at all, so we don't even need to upload them to the graphics card unless they are on the screen. And furthermore, if we zoom out, I said zoom out, stupid mouse will thanks. Now we might as well just use a single zoomed out tile. Say we have a single tile which is all of this, but pre-scaled to this size. Now we don't need to render 4 tiles, now we only need to render 1 tile which has already been pre-scaled, so it doesn't contain as much data. And well, that's a fairly easy thing to do in C++, and it is what I was doing anyway in the original data you saw. Yeah, there you just gotta look into the script of this video. Anyway, you saw a loading bar there. That's because it was loading all the individual tiles. I created a C++ program which automatically splits this gigantic texture into 32 by 32 tiles, and then zooms everything out and scales it and cuts it into 16 by 16 tiles, and then zooms out again and cuts it into 8 by 8 tiles, then zooms out and cuts it all into 4 by 4 tiles, then zooms out and cuts it all into 2 by 2 tiles, and finally zooms out and creates just a single tile. And here at the top of the screen you can actually see how many tiles are currently being rendered and currently uploaded to the graphics card. Now we just have 1 tile. Now we have our 2 by 2, so 4 tiles. Yeah, we briefly had 8 by 8 tiles, and if we zoom further in, we are only displaying the tiles which are actually on the screen, and that's how I can move around this map and zoom in and zoom out, and everything is almost smooth. There is some frame stuttering when we zoom in and out because the program needs to upload the new tiles to the graphics card and remove the old tiles from the graphics card. And sadly that all has to happen in the main thread, so there can be no multi-threading. That's just a quirk of the SGL library I'm using for graphics. All graphics related things need to happen in a single thread, the same thread the graphics renderer was initialized in. So there isn't much we can do about that slight bit of lag, but it's not too bad. And well, this is the finished product. Oh, one more thing to say. You remember that water map and that river map I made? Yeah, I have also loaded that as a texture in the background, and I'm using that to check whether the ball is on land or in water. And I'm using a mix of the water map and the height map to determine how quickly the ball is able to move. Anyway, I just randomly decided to do the rest of the video in one take, so I am afraid the video is over. You can, well, that's a good thing, you can go now. Let's just get the ball to Helgoland. Is this Helgoland or is that Helgoland? I think this is Helgoland. Okay, maybe Helgoland is too small to register as land. Whatever. You can go now. And when you leave, feel free to hit any of those random buttons down there. They don't do anything, but it might still be satisfying to click something. I said you can go now. Jeez, they're still here. Okay. Why? The video is over.